Have you ever looked up on a clear night and felt the vastness begin to press in? We often think we know our neighborhood, the predictable dance of our planets, the steady light of our Sunday. Yet, past the familiar edge of our solar system, the rules seem to change. It's a transition from the known to the truly strange. Imagine standing on a threshold. Behind you, everything is cataloged, mapped, and understood. Ahead, something is definitely there, something massive, perhaps even a world we can barely comprehend, exerting an invisible pull on everything we thought was stable. It's not a ghost story. It's a gravitational truth, hinted at by subtle wobbles in distant icy orbits. This isn't just about planets. It's about the deep, unexpected structures that govern our cosmic backyard. If that quiet, unfolding mystery speaks to your curiosity, a gentle like and subscribe helps us keep exploring these edges together. Settle in. Let's find out what secrets are hiding just beyond the reach of our current maps. The event that forged our local cosmic neighborhood was not a slow, steady change. It was an act of profound and overwhelming violence. Picture not just one, but 15 massive stars reaching the end of their lives, collapsing inward before exploding outward as supernovae. When these powerful events occur clustered together, both close in terms of physical space and relatively close together across millions of years, the result is a truly spectacular cosmic upheaval. It is an event that fundamentally reshapes the structure of the space surrounding it, pushing material aside with staggering force. The cumulative power of these near simultaneous blasts created something monumental, a vast, sweeping void in the fabric of the interstellar medium, the gas and dust that fills the space between stars. This void, now known as a hot bubble, is essentially a monumental area of space that has been aggressively cleared of most of its matter. The raw force from the explosions, a collective, relentless punch, sent massive shock waves tearing through the surrounding galactic material. These shock waves continue their journey even now, hurtling across our galaxy at phenomenal speeds, estimated to be around 6 kilometers per second, 6,000 meters per second. As these shock waves traveled, they did two critical things. They swept the interstellar dust and gas out of the way, carving out the immense cavity, and they dramatically heated the remaining, extremely sparse gas within the bubble. The material left behind in this bubble is plasma, a superheated gas where electrons have been stripped from their atoms, reaching temperatures that can soar to 1 million degrees Celsius. 1 million degrees, written as a 1 followed by 6 zeros, Celsius. This process of simultaneously creating a massive, low-density hole, often compared to creating holes in Swiss cheese and heating the gas within it, is exactly what defines a hot bubble. It is a dual process that marks both a dramatic cosmic ending, the death of giant stars, and a spectacular beginning, often leading to the compression of matter at the edges that triggers the birth of new stars. Crucially, this is not a structure we are merely observing from afar. We are not heading toward it from the outside. Our entire solar system, including the Earth, the Sun, and all the planets, is currently inside this monumental structure. We are effectively traversing its massive interior, charging headfirst toward the very point in space where the original explosions occurred. Welcome to our local hot bubble. This bubble represents the actual, immediate neighborhood of space surrounding our solar system, the local environment we exist within. While we are still actively mapping and exploring this neighborhood, its defining characteristics and its powerful origin story are becoming increasingly clear to scientists. So, the core questions we must explore are: what are the established facts about the local hot bubble? How precisely did it manage to form? And what more is left to discover within this million-degree void that we call home? The realization that our solar system resides within such a colossal structure did not happen overnight. The existence of the local hot bubble was a concept that was not always certain. The first major step toward identifying it occurred in the 1970s through observations made across the entire sky. Scientists detected diffuse, low-energy X-ray emissions, seemingly emanating from everywhere at once. These X-rays hinted at a huge volume of extremely hot, thin gas permeating the surrounding interstellar medium. Based on this evidence, scientists hypothesized that this must be a vast cavity, a superbubble, filled with this tenuous, million-degree gas. However, the scientific picture soon became complicated. By the 1990s, further research introduced a challenge to this original hypothesis. Scientists found that similar low-energy X-ray emissions could actually be generated in other places, specifically wherever neutral atoms without an electrical charge, came into contact and interacted with the solar wind, the continuous stream of charged particles flowing outward from our sundae. This finding suggested that the X-ray emissions might not necessarily point to a large, faraway hot bubble, but instead could be produced much closer to home within our own solar system. This ambiguity required a definitive, focused observation. The evidence that eventually solidified the original idea, confirming the presence of a vast, hot bubble, arrived later. In 2014, the National Aeronautics and Space Administration, NASA, effectively confirmed the existence of the local hot bubble using data from the DXL mission, short for the diffuse X-ray emission from the local galaxy mission. While it is true that background, soft X-ray radiation can originate from various sources, for example, from materials in comets interacting with the solar wind as they pass through our inner system, the DXL mission provided a critical distinction. It determined that only about 40% of the total amount of low-energy X-ray fog detected originated from within the confines of our own solar system. This finding strongly affirmed that the dominant source, the remaining 60%, had to be diffuse X-ray emissions coming from that specific million-degree region of interstellar plasma, the structure we now confidently call the local hot bubble. Although this observation definitively confirmed the cavity, it left critical questions unanswered. What immense force could possibly create such a massive void in the interstellar medium? Furthermore, what could explain the thousands of relatively young stars that appear to be concentrated around the edges of this bubble? The most compelling answer that emerged from subsequent research was one of both overwhelming power and incredible scientific detail. The prevailing model now strongly suggests that the local hot bubble is the direct aftermath of a chain of roughly 15 supernova explosions. These stars did not all explode simultaneously, but occurred sequentially within a relatively short cosmic timescale, a span of a few million years, and in close geographical proximity to one another in space. Scientists estimate that the very first of these colossal stellar explosions took place approximately 14 million years ago. Each explosion released truly enormous amounts of energy. This expelled energy, along with the superheated material ejected by the dying stars, acted like a massive bulldozer, continually pushing the surrounding interstellar matter farther and farther out, while simultaneously heating the relatively sparse gas that remained trapped within the cavity to those extreme temperatures. The key to understanding this ancient sequence of violence is that the evidence of these explosions has been meticulously preserved in a remarkable place, Earth's own geological record. Scientists have found clear traces of these ancient cosmic events in deep-sea sediment deposits, the layers of mud and material that build up slowly on the ocean floor over millions of years. This evidence comes in the form of a specific, rare radioactive element called iron-60, written as the chemical symbol Fe, followed by the number 60. This particular radioactive isotope can originate from a few different astrophysical sources, but the most common and plentiful source is widely believed to be the colossal shock waves produced during supernova explosions. The reason we are confident that the source of this iron-60 is truly extraterrestrial is straightforward. The Earth itself, through its natural geological or atmospheric processes, has no way of producing iron-60 on its own. Furthermore, matching deposits of this isotope have also been discovered on the Moon, independently confirming its cosmic origin. What makes iron-60 so incredibly valuable to researchers is that we know precisely how long its half-life is, the time required for half of a given amount of the radioactive element to decay into a more stable form. We know that iron-60 first undergoes radioactive decay, transforming into another radioactive isotope called cobalt-60, CO60, before cobalt-60, in turn, decays into nickel-60Ni60, which is a completely stable element. Iron-60 has a half-life of 2.6 million years, 2,600,000 years. In comparison, cobalt-60 has a much shorter half-life of only about 5.3 years. Because these decay rates are known and constant, when scientists discover a deposit containing these specific elements, they can compare the relative amounts of iron-60, cobalt-60, and nickel-60 present. This comparison acts as a kind of elemental clock, allowing them to precisely reveal when that cosmic material first settled and was deposited onto our planet. Fortunately for us, the geological record of these ancient cosmic catastrophes is not hidden. It has been found across the globe. Over the past 2 decades, international research teams have successfully located and analyzed several such deep-sea deposits that contain the telltale signature of iron-60. The confirmation of this debris field was a major scientific milestone. Specifically, in 2016, scientists reported a breakthrough after analyzing deep-sea crust samples meticulously collected from 3 of the world's major oceans: the Pacific, the Indian, and the Atlantic Oceans. The fact that the deposits were found scattered across such massive geographical areas on Earth only strengthened the case for a truly colossal external source. The analysis of these samples was particularly revealing because it indicated 2 distinct, separate increases, or spikes, in the amount of radioactive debris found in the sediment layers. These spikes directly pointed to multiple supernova events that had occurred in our not-too-distant cosmic past. By using the known half-life of iron-60 as a precise clock, the teams were able to date these events with remarkable accuracy. The more recent layer of debris showed a significant spike in iron-60 that spanned the period between 1.7 million years ago and 3.2 million years ago. The older spike, indicating a previous series of events, was dated much earlier, falling roughly between 6.5 million years ago and 8.7 million years ago. All of this material appears to have originated from a region of space located approximately 326 light-years away from our solar system. Dr. Anton Wallner, a nuclear physicist who led one of the key research teams studying these unique deposits, highlighted the critical implication of the more recent event. He noted that the fact that this newer layer of supernova debris was not instantaneous, but rather spread across a time frame of approximately 1.5 million years from 1.7 million years ago to 3.2 million years ago, powerfully suggested that this was not a single, isolated explosion. Instead, it was clear evidence of a series of supernova events that must have occurred sequentially, one after the other, in relatively quick succession on a galactic timescale. Following this crucial finding, a second team of scientists, led by astrophysicist Dr. Dieter Breichfeld, set out to identify the likely origin point of these explosive events. Their research narrowed down the possible locations of the supernovae that created our local hot bubble to a region that was between 196 and 423 light-years from the Sun at the time of the explosions. The scientific consensus suggests that these stars that exploded to create our local hot bubble were likely part of an aging stellar cluster. The surviving members of this original star group are now strongly associated with a vast collection of young stars known as the Scorpius-Centaurus stellar group, a major association of hot, bright, massive stars that share a common origin and movement through the galaxy. Using the forensic data provided by the Iron-60 deposits, Dr. Breichfield's team was able to specifically pinpoint the signals of two major supernovae within the more recent spike, one that occurred approximately 1.5 million years ago, and a slightly older one that happened about 2.3 million years ago. Their analysis of the decay products further allowed them to estimate the initial mass of the stars responsible for these blasts. The star that exploded 1.5 million years ago was estimated to have been roughly 8.8 times the mass of our own Sun, and the one that exploded 2.3 million years ago was even larger, estimated at 9.2 times the mass of the Sunday. These were truly giants, destined for a catastrophic end. This powerful series of explosions carved out the void we inhabit, but the process of reshaping the cosmos did not simply stop when the explosions ended. In fact, our local hot bubble is still growing today. While it is certainly expanding at a much, much slower rate than it was immediately following the supernovae millions of years ago, the edge of the bubble continues to creep outward. The current speed of this expansion has stabilized or plateaued at about 6 kilometers per second, 6,000 meters per second. This expansion is the key to understanding the next critical piece of the puzzle, the massive number of young stars we see nearby. In 2022, astrophysicist Dr. Catherine Zucker authored a groundbreaking research paper that provided a comprehensive reconstruction of the evolution of our galactic neighborhood. Her work meticulously traced the chain of cosmic events that not only created our local hot bubble, but also directly led to the formation of all the young, nearby stars and star-forming regions visible today. The incredible foundation for this discovery was data provided by the European Space Agency's Gaia telescope. This revolutionary orbital observatory is dedicated to measuring the precise three-dimensional positions and three-dimensional motions of approximately 2 billion stars in our galaxy. Using this vast, precise dataset, Dr. Zucker and her team were able to construct a detailed three-dimensional space-time map. This is far more than just a snapshot. It is a dynamic model that allowed them to rewind and observe how objects near our solar system moved and interacted over millions of years. The resulting map revealed an incredible and definitive discovery. Within a distance of 500 light-years from our planet, essentially all of the young stars and the regions where new stars are actively forming do not exist randomly. Instead, they reside directly on the surface or the outer shell of our local hot bubble. The implications of this visual and mathematical mapping were immediately clear. By tracing the 3D positions and the 3D movements of these stellar clusters backward in time for 20 million years, the scientists confirmed that the well-known star-forming regions near our solar system did not just happen to form near the bubble. They formed precisely along the outer edge of the local bubble as it swept up gas during its relentless outward expansion. These regions, known as stellar nurseries, are vital areas of scientific study. They are giant, cold, dense clouds of gas and dust, where gravity can finally overcome the internal pressure of the gas, causing the material to collapse and ignite new stars. We are continually learning more about these nurseries, especially as new, incredibly detailed images are captured by our most powerful, ground-based, and orbital telescopes. Consider for a moment the Shyamalan-1 dark cloud. This is one of our very nearest stellar nurseries, a place where a new generation of stars is currently being born. Here is a spectacular image of this cloud, captured by the dark energy camera, which is mounted on the Victor M. Blanco 4-meter telescope at the Cerro Tololo Inter-American Observatory. By studying how the light from stars deep inside these dark clouds changes as it travels towards us, scientists can carefully extract crucial details about the density, temperature, and movement of the gas. This information, combined with the detailed model of the local hot bubble, helps us better understand the direct, active impact of the bubble's expansion on the star formation history of our galaxy today. The bubble is not just a relic of the past, it is a factory for the future. Based on the birth of the local hot bubble, which started approximately 14 million years ago, Dr. Zucker and her colleagues were able to identify 4 distinct periods, or epochs, of star formation that were directly triggered on the shell of the expanding bubble. The earliest epoch they identified began around 16 million years ago. During this time, we see the birth of the Upper Centaurus lupus, often abbreviated as the UCL star cluster, a group of young stars that were gravitationally bound together. This was quickly followed by the formation of the Lower Centaurus crux, the LCC star cluster. These 2 significant stellar populations formed at a cosmic distance of about 49 light-years apart from one another. Crucially, it was these early stellar populations, which formed in the wake of previous compressions, that subsequently supplied the massive stars, the 8.8 and 9.2 solar mass giants, that eventually went supernova and provided the energy to truly create and expand our local hot bubble around 14 million years ago. The expansive force of the supernovae was so great that it systematically compressed the surrounding galactic material, leading to a chain reaction of stellar births over millions of years. Following the initial destruction that formed the local hot bubble LHB around 14 million years ago, Dr. Zucker and her team traced 4 distinct periods of star formation that were triggered by the bubble's ongoing expansion. The first of these 4 star-forming epochs occurred approximately 10 million years ago, as the bubble's edge, moving at many kilometers per second, slammed into the denser, cooler interstellar gas. The tremendous pressure initiated a gravitational collapse within these clouds. This epoch saw the birth of the Upper Scorpius Association, a relatively young group of stars, along with other older populations of stars that were pushed into existence by this expanding cosmic wall. Then, roughly 6 million years ago, the bubble's expansion triggered the second star-forming epoch. This period gave rise to star clusters like Corona, Australis, and the older stellar populations found within the Taurus molecular cloud complex. Imagine the bubble's surface acting like a massive, invisible snowplow, sweeping the raw material of the galaxy, the cold hydrogen and dust, into dense, concentrated ridges where gravity could then take over to forge new suns. The third epoch followed around 2 million years ago. By this time, the pressure waves had moved farther out, leading to the creation of the stars in the Lupus and Chamaeleon star-forming regions. This epoch also saw the birth of the younger stellar populations within the Taurus complex, as well as the Ophiuchus star-forming region. These events demonstrate that the process is not a single, sharp impact, but a continuous, long-term effect, where the bubble's perimeter keeps causing sequential collapses as it expands into new, undisturbed territory. Finally, our present time falls within the fourth star-forming epoch. The process is not over. Today, we can observe the presence of dense molecular gas, the raw fuel for star formation, still actively clustering around the perimeter of the local hot bubble. This accumulating, compressed gas will inevitably lead to more star clusters being born along the bubble's outer edge in the future, meaning the consequences of those ancient supernovae are still actively shaping our galactic landscape. With all this intense, localized stellar creation along the bubble's boundary, it might come as a surprise to realize that our own sun is something of an interloper in this neighborhood. Our star did not form inside the local hot bubble. The sun formed far away, about 978 light-years distant, when the first sequence of supernovae occurred in the UCL and LCC star clusters. Our solar system has always been on a long, slow orbital path around the galactic center, and it was that path that eventually brought us into the local hot bubble. The sun only joined the LHB approximately 5 million years ago, drifting into the cavity as its trajectory through the galaxy intersected with the bubble's massive volume. If you visualize the path of our sun, tracing its movement backward in time, the yellow dots show the sun's position just before it finally entered the bubble. And now, purely by cosmic coincidence, the result of its long journey around the galaxy and the bubble's vast size, our sun happens to be currently situated near the very center of the LHB. We are now passively drifting through the heart of what was once a raging furnace. This unique location has naturally spurred scientists to become deeply interested in accurately mapping the ongoing temperature and properties of the gas within the local hot bubble. This brings us to a fundamental question. Why are we so calm about being inside a bubble where the plasma temperatures can reach 1 million degrees Celsius? 1 million degrees. The answer lies in the concept of density. The three-dimensional map derived from Dr. Zucker's 2022 publication shows the vast extent of our local hot bubble. The gas inside this dark blue region is superheated, but its density is extraordinarily low. This gas contains about 100 times less hydrogen than the typical average interstellar medium found elsewhere in the galaxy. Think of it this way. Temperature is a measure of how fast the individual particles are moving. At 1 million degrees Kelvin, which is almost exactly 1 million degrees Celsius, the particles of gas are indeed moving incredibly fast, and when they strike a detector, they generate the diffuse X-ray emissions we observe across the sky. However, density is a measure of how many particles there are in a given space. Because the density is so incredibly low, it is practically a vacuum. There are simply too few super fast moving particles to transfer any significant amount of heat to our solar system. The chance of a 1 million degree particle hitting our spacecraft or planet is extremely remote. So, while the temperature of this gas soars to about 1 million degrees Kelvin, giving rise to those telltale diffuse X-ray emissions. We have absolutely nothing to worry about in terms of being boiled alive. Tracking these temperatures and mapping the X-ray emissions have provided crucial, ongoing confirmation of the bubble's existence and structure. The most detailed all-sky survey of soft X-rays to date has been provided by the eRosita X-ray telescope. The name is an acronym, standing for the Extended Roentgen Survey with an Imaging Telescope Array. Launched in 2019 aboard the joint Russian and German mission named Spectrum Roentgen Gamma, or Spectre-RG, eRosita has given scientists an unprecedented, detailed view of the hot gas permeating the cosmos. The data collected by the eRosita X-ray telescope allowed a team of scientists led by the Max Planck Institute for Extraterrestrial Physics to create a sophisticated, highly detailed three-dimensional map of the LHB. This map not only confirmed the bubble's boundary, but also revealed a fascinating detail: a temperature gradient. The galactic south region was found to be slightly hotter than the galactic north region. This subtle but significant temperature difference could potentially be explained by a final, isolated series of supernova explosions that occurred more recently, perhaps within the last few million years, providing a slightly hotter boost of energy to one hemisphere of the bubble compared to the other. By creating this refined bubble map, the eRosita team also discovered that the local hot bubble is stretched out. It is not perfectly spherical. It extends significantly toward the poles of the galactic hemisphere. This asymmetrical shape has a simple physical explanation. The hot gas within the bubble naturally expands outward in the direction that offers the least resistance. Since the Milky Way's galactic disk contains the densest concentration of cold gas and matter, the path of least resistance for the hot plasma is away from the plane of the galactic disk, leading to its elongated, polar stretched shape. Compiling this new data, including temperature variations, the precise shape of the bubble, and the detailed X-ray emissions, the team created an even more intricate map of our immediate galactic neighborhood. In this new three-dimensional map, our local hot bubble looks less like a single, isolated feature and more like a three-dimensional splatter, heavily surrounded by, and even overlapping with, other galactic structures. These other neighboring structures represent known remnants of powerful supernovae, such as the famous Gum Nebula shown in the map in a prominent red color and various dense molecular clouds, often highlighted in orange. The data gathered from eRosita and the work by Zucker strongly suggest that these colossal superbubbles are likely a common feature throughout our entire galaxy. This leads to the compelling idea that the Milky Way itself resembles a kind of Swiss cheese. The vast, low-density cavities, or holes, of this galactic Swiss cheese are violently blasted out by the gigantic energy releases of supernova explosions, with new stars continually forming along the compressed edges of the holes created by the dying older stars. And, just like Swiss cheese, it appears that some of these superbubbles may not be isolated. They may have tunnels or openings connecting them to other bubbles or other larger galactic structures. This suggests that our local hot bubble may not be a solitary entity, but rather part of a complex and intricate network of similar features threaded throughout our galaxy. A prime example of this connectivity is the Canis Major Tunnel. This structure lies on the plane of the Milky Way's galactic disk and is believed to act as a connection point, linking our local hot bubble to the nearby Gum Nebula, or perhaps even a larger superbubble that encompasses the Gum Nebula. Furthermore, the new 3D map revealed another, previously unknown interstellar tunnel stretching outward toward the constellation Centaurus. This newly discovered feature potentially connects our local bubble to the neighboring Loop 1 superbubble. While these interstellar tunnels are extremely tantalizing pieces of evidence suggesting a massive, interconnected plumbing system of hot gas, our current understanding of their full extent and mechanics remains limited. Nevertheless, the discovery of this complex system, these colossal tunnels of hot gas and bubbles of star formation shaped by the death of gigantic older stars, fills us with awe. It underscores just how powerful and interconnected the evolution of our local galactic neighborhood truly is. The science suggests that stars are not simply born and destined to die in isolation. Instead, their energetic output, particularly the cataclysmic energy released during their deaths, continues to mold and shape the environment for millions of years after their demise. As our observational tools and sophisticated analysis techniques, like those used by Gaia and Erosita, become more refined, we are only beginning to uncover the true extent of these hidden, immense structures. So, the next time you look up at the night sky, you might take a moment to remind yourself that we are not drifting in a calm, empty void. We are surrounded by crazy, dynamic patterns, a vast hole in the Milky Way that was violently carved out by ancient cosmic cataclysms. And remember that some of the beautiful stars you see twinkling above are not just distant pinpricks of light. They are actually plastered along the massive superheated walls of a supernova-blasted cavity, a cavity that likely connects to other parts of the galaxy through intricate, unseen interstellar tunnels. Imagine for a moment a sight of unimaginable cosmic power unfolding just outside the familiar boundaries of our stellar neighborhood. You are looking out into the night sky, and suddenly, a single, incredibly bright light flares violently into existence. This sudden, dazzling star rapidly grows in luminosity, potentially becoming as bright as the full moon in the night sky, and remaining clearly visible even during the day. If you can see this catastrophic light show, you might already be in profound danger. This unexpected celestial event is the violent death of a massive star, and it is known as a supernova. The danger from such an event comes not just from the light we see, but from the initial, focused burst of high-energy radiation. This newly detonated star is flooding Earth's atmosphere with a catastrophic dose of gamma radiation and X-rays. Gamma rays, the highest energy form of light, would strip away a significant portion of our planet's protective ozone layer, that thin, vital shield in the stratosphere that absorbs most of the sun's harmful ultraviolet radiation. With the ozone layer significantly depleted or destroyed, life on Earth would be exposed to the full, unmitigated fury of the sun's deadly ultraviolet radiation, leading to mass extinction and devastating environmental consequences. Simultaneously, following that initial flash of lethal radiation, a monumental wave of stellar matter and debris is jettisoned outward at terrifying speeds. This cosmic ejecta travels at velocities ranging from 10,000 kilometers per second, 10,000 meters per second, up to 40,000 kilometers per second, 40,000 meters per second. To put this speed in context, the fastest man-made spacecraft currently travels at a tiny fraction of that speed. This is the dying roar of the exploding star, venting billions of tons of superheated mass toward our planet, ready to sweep across Earth's magnetic field in a tidal wave of superhot particles and shock waves. This is one interpretation of the catastrophic scenario we might face if a supernova were to occur too close to us. This raises crucial and necessary questions that bridge the gap between abstract cosmology and our immediate environment. How likely is it for this kind of event to actually happen near Earth? What on a cosmic scale actually constitutes near us? And precisely how close would a supernova blast have to be before the potential for catastrophe, the stripping of the ozone layer, and the subsequent environmental collapse would genuinely threaten life on Earth? Finally, what specific, massive stars in our vicinity have the potential to detonate in this way? Let us begin with the fortunate news. Supernovae are not, in the grand scheme of things, a common occurrence within our own galaxy. While astronomers observe hundreds of supernovae every single year, these events are seen scattered across the vast expanse of the observable universe. This high rate of detection is primarily a reflection of the sheer, overwhelming number of galaxies that exist in the cosmos, each containing billions of stars. Closer to our cosmic home, within the confines of our own Milky Way galaxy, the rate drops dramatically. We are only likely to witness about 2 to 3 supernova explosions every century, a period of 100 years. This calculation is based on tracking the rate of star death in the Milky Way and adjusting for the fact that a large portion of the galaxy's explosions are obscured from our view by thick, intervening dust and gas. This means the statistical odds of one going off directly in our vicinity tomorrow are comforting low. However, low odds are not the same as impossible. According to geologists and archaeologists, the planet Earth has almost certainly been struck by the effects of a supernova blast before in the course of its long 4.5 billion years of existence. For one, our entire local region of space, the area we are currently discussing, is evidence of such an event. We exist within the local hot bubble, a comparatively sparsely populated region of interstellar space, extending about 1,000 light-years across. Scientists strongly believe this entire massive cavity was carved out by a sequence of supernova detonations that occurred between 10 and 20 million years ago, a time when our planet was certainly present and orbiting the Sunday. Beyond the creation of our current neighborhood, scientists have found definitive evidence of a more recent, closer detonation. This evidence points to a supernova that occurred approximately 2.5 million years ago. The telltale sign is a highly concentrated layer of exotic isotopes found within a specific layer of the Earth's geological record. These isotopes include the previously mentioned iron 60 iron, followed by the number 60, and a different isotope, manganese 53 manganese, followed by the number 53. The presence of both these elements, which are created in the nuclear fires of exploding stars, provides a scientific fingerprint identifying the event. Thankfully, the calculations show that this supernova happened far enough away, likely hundreds of light years, to have been completely harmless to life on Earth. But the question of proximity remains unsettled, and some scientists posit more radical, closer impacts. There is ongoing debate among certain research groups who believe that a massive piece of debris from a supernova, potentially a fragment of the shockwave, may have crashed into the planet around 13,000 years ago. Some evidence supporting this theory comes from a particular impact site that contains anomalies like magnetic spherules and elevated levels of the radioactive substance, potassium-40 potassium, followed by the number, a substance known to be found in the violent ejecta expelled by a supernova. This timing aligns closely with the major extinction event that saw the demise of the woolly mammoths. Even preceding that theoretical impact, physical evidence of cosmic debris has been found. Mammoth tusks dated back 34,000 years were discovered containing tiny impact craters left by microscopic grains of slightly radioactive iron. Critically, analyses showed that these grains must have been traveling at speeds around 10,000 kilometers per second, 10,000 meters per second. As you might recall, This speed falls precisely within the potential range of velocities calculated for supernova explosions. While this direct impact of tiny grains was likely an unpleasant experience for the mammoths, it was far from lethal on a large scale. An astute observer might note an important, reassuring fact from this historical record. If life originated on Earth approximately 3.7 billion years ago, and we have faced at least 3 major, confirmed or hypothesized, supernova events that have directly impacted our planet or our solar neighborhood in just the last 20 million years, the sheer continuation of life suggests a fundamental truth. Despite the extinction of the woolly mammoths and other past events, which we should not minimize, supernovae as a whole cannot be quite as universally destructive as the initial catastrophic introduction might make them seem. And this is largely true. The critical variable in the equation is always proximity. The sheer distance involved is the primary defense. If you are 1,000 kilometers away from a nuclear detonation, you have very little to fear from the heat and immediate blast wave. However, the story is entirely different if that same device were to detonate right on your coffee table. When it comes to supernovae, the sheer scale of the universe means that we have, metaphorically speaking, a relatively large distance of safety separating us from potential cosmic disaster. To understand the actual risk and the scale of these enormous explosions, it is absolutely necessary to understand the immense forces involved. This means we must first gain a better, clearer understanding of the physical processes that lead to a supernova. It turns out there are primarily 2 main paths that a star can take to reach that spectacular, explosive, grand finale known as a supernova. However, in either case, the star must possess specific physical properties. It has to be the right kind of star to begin with. The first pathway leads to what scientists classify as a Type 1, a supernova. This type of explosion typically occurs within a binary star system, where 2 stars are gravitationally bound and orbit a common center. Specifically, this path usually involves a white dwarf, the super-dense remnant of a sun-like star that has exhausted its nuclear fuel. This white dwarf is often found gradually, or sometimes quite rapidly, siphoning and stealing matter away from its neighboring companion star. This theft continues until the white dwarf reaches a point of critical mass. This particular path to explosion involves a delicate, highly energetic balancing act between 2 incredibly powerful, opposing cosmic forces. A white dwarf is essentially a dense star composed mostly of carbon, which behaves like a giant, super-compressed diamond core. It is normally held in a fragile balance between gravity, the force seeking to crush it inward, and electron degeneracy pressure, the force resisting that crush. To understand degeneracy pressure simply, atoms fundamentally resist being squashed too tightly. The electrons orbiting the nucleus of an atom adhere to quantum mechanical laws that dictate they cannot occupy the exact same space and state as another electron. They prefer to maintain certain distances from the nucleus. This internal resistance from the electrons against being compressed beyond a certain point is the electron degeneracy pressure. But gravity is an overwhelmingly powerful force that seeks to draw matter continually closer, especially when dealing with a mass as dense as a white dwarf. In these relics, a section of matter the size of a common sugar cube can have a mass equivalent to that of a car on Earth. In a binary system, as the white dwarf relentlessly absorbs more and more mass from its companion star, the total weight, or mass, begins to overwhelm the stabilizing force of the electron degeneracy pressure. Eventually, when the white dwarf's mass surpasses a specific theoretical limit known as the Chandrasekhar limit, which is about 1.4 times the mass of our sun, the electron degeneracy pressure collapses. The entire structure of the star buckles inward at once. This sudden, catastrophic implosion generates enormous heat and pressure, instantly triggering the fusion of carbon throughout the entire star's core. Within a fleeting few seconds, almost the entirety of the star undergoes runaway fusion. The carbon transforms violently into heavier elements, primarily nickel and iron, and in doing so, releases an incomprehensible amount of energy as the star's matter settles into its slightly more efficient, new nuclear configuration. How much energy are we talking about? The sheer scale is difficult to grasp. Approximately 1/4 rotillion joules, written as the number 1, followed by 45 zeros. This colossal release of energy happens in the blink of an eye, over the course of just a few seconds. Naturally, this immense internal pressure causes the star to completely eject its entire contents outward in all directions. The stellar material is sent traveling at extreme velocities, reaching speeds of up to 6%, the speed of light, 6% of 299,792 kilometers per second, and unleashing a devastating flood of high-energy light, mostly in the form of gamma radiation, across the galaxy. The resulting visible event is phenomenally bright. The supernova can briefly shine with a luminosity that is 5 billion times brighter than our own Sunday. This intense visible light fades gradually over a few weeks, continuing until the stellar ejecta has traveled far enough that the overall energy level and density have begun to dissipate into the wider interstellar medium. White dwarfs are usually completely obliterated in this process, vanishing entirely. The second type of supernova, known as a Type 2 supernova, follows a similar overall catastrophic pattern, but the mechanism is different. Instead of involving a white dwarf in a binary system, this explosion involves a single, massive star, a star that must be at least 5 times more massive than our sun at the end of its life. In these immense stars, they are still burning brightly, fusing elements in their core. Their balance against the inward crushing force of gravity is maintained not just by electron degeneracy pressure, but also by the enormous outward pressure generated by the heat of nuclear fusion. However, just like the Type 1a event, this balance eventually collapses. This time, the collapse occurs because the massive star simply runs out of fuel. Specifically, it runs out of lighter elements to fuse and begins to create iron in its core. Iron cannot be fused to release energy. It actually consumes energy. Without the additional, continuous outward push of fusion energy, the weight of the massive star's outer layers, which is truly colossal, is too much for the electron degeneracy pressure alone to manage. To a similar ultimate effect as the white dwarf, the star's core collapses. The core violently shrinks and condenses, quickly reaching the density of an atomic nucleus. The collapse is so abrupt and so powerful that the outer layers of the star suddenly slam into this incompressible, super dense core, creating a massive rebound shockwave that tears through the star. This shockwave is what drives the massive star's outer layers into space as a Type 2 supernova. The key difference here is the remnant. While the outer layers are ejected, the remaining core often survives, collapsing further down into either an extremely dense object called a neutron star, or, if the initial star was massive enough, a black hole. In either case, the scale of material and the sheer energy released by a supernova is truly vast. Unsurprisingly, anything immediately next to such an explosion is not going to last for long. This is an energy release powerful enough to completely rip apart a star, or at least a significant portion of it. A small, non-self luminous object like a planet would stand absolutely no chance if it were within the immediate vicinity. Our own sun, thankfully, will never go supernova because it simply is not massive enough. It will instead become a gentle white dwarf. But if our sun were somehow massive enough to detonate, there is a very high probability that Earth would be either partially or completely vaporized. The sudden, immense thermal energy would cause Earth's rocky exterior to reach a boiling point, with temperatures soaring up to 15 times hotter than the current surface of our Sunday. The Earth's material would then be swept away and dispersed by the powerful shock waves and stellar ejecta passing in the weeks following the supernova blast. What is perhaps surprising, however, is the rate at which the most intense, immediate wave of physical devastation, the vaporization, would dissipate with distance. In 2011, experts from the University of Cambridge calculated that even planets orbiting their star at a distance of 15 billion kilometers, 15,000 million kilometers, a distance about 100 times greater than the massive distance between the Sun and the Earth, would actually remain physically intact. These surviving planets would not be destroyed, but they would simply be sent hurtling out into interstellar space, now that there was nothing substantial left to orbit. Of course, the hypothetical ecosystem of such a planet would instantly face far more significant problems. Even without being physically vaporized, the planet would get extremely cold very quickly due to the sudden lack of a heat source. And even if the crust of a planet remained physically intact, that does not mean that life, as we understand it, would be sustainable. Setting aside the sheer visual shock, the light of a nearby supernova can briefly outperform the brightness of an entire galaxy, potentially causing immediate and permanent blindness for anyone who happened to look at it. The true long-term threat to life is the atmosphere. The primary mechanism for extinction is the stripping away of our protective atmospheric layers. High-energy radiation, specifically the initial burst of gamma rays and X-rays, would not need to affect us directly at the surface to be lethal. Instead, the radiation would drastically alter the chemical composition of our upper atmosphere. This radiation would annihilate the ozone layer, which is made of a specific combination of oxygen atoms, turning it into nitrogen oxide compounds and other substances. This change would effectively negate our ozone layer. With the ozone shield gone, life on Earth would face the full blast of the sun's ultraviolet radiation, vastly increasing the odds of death from radiation poisoning and cellular damage, leading to massive rates of mutation. More catastrophically, the sudden influx of UV radiation would immediately kill off the phytoplankton, the microscopic plants at the base of the marine food web in the upper layers of the oceans. The consequences of this immediate loss would cascade rapidly up the food chain, resulting in global mass extinctions. Based on these atmospheric and biological threats, scientists place the critical kill zone, the distance within which a supernova poses a near certain existential threat to complex life on a planet like Earth, at around 25 light years. Beyond this distance, the deadly energy bursts are generally attenuated enough by interstellar space to pose a significantly diminished threat beyond that critical safety boundary of 25 light years. 25 light years, the truly devastating fury of a supernova begins to calm down dramatically. Distance acts as a highly effective cosmic buffer, causing the energy and radiation to wear itself out and dissipate. At greater ranges, the intense X-rays and gamma rays are significantly absorbed by the vast, sparse expanse of interstellar gas and dust before they can reach our atmosphere in critical amounts. However, science often presents exceptions that defy the general rule. The scenario involving the asteroid or debris that potentially caused the extinction of the woolly mammoths is believed to have originated from a supernova event located as far as 250 light-years. 250. If this particular theory is accurate, it highlights a crucial point that the catastrophic outcome was likely a matter of extreme bad luck, perhaps a direct hit from a large, solid fragment of the stellar core rather than the radiation itself. Generally speaking, we would not expect to notice any significant damage, certainly not damage leading to mass extinction, from a supernova occurring at this distance. The radiation levels would simply not be high enough to break through our atmospheric defenses. By the time we consider an event occurring at 500 light-years, 500 light-years away, we would hardly notice the explosion at all, other than perhaps seeing a genuinely spectacular brighter star in the sky for a few weeks or months. This means that the true existential threat level is strongly tied to the most immediate local vicinity. This leaves one essential, immediate question. Within a dangerous radius of, say, 300 light-years? 300 light-years? Are there any confirmed supernova candidates that we need to actively worry about? Fortunately, the answer, according to modern astrophysical data, is a confident no. Massive, short-lived stars are not subtle. They are incredibly bright and noticeable, making them relatively easy for astronomers to track and monitor. Within our critical safe radius, the only two truly massive stars that are currently considered to be at risk of going supernova in the foreseeable astronomical future are Betelgeuse, often pronounced Beetlejuice, and Antares. Both of these stars are colossal red giants, nearing the end of their lives, but both are safely located at a distance of more than 400 light-years away. The other major type of threat, the white dwarfs that cause type 1a supernovae, are a little trickier to monitor due to their compact size and the fact that they have significantly diminished their brightness since their main life stage. They have historically been conventionally difficult to spot. This diminished brightness makes it harder for scientists to predict accurately whether we might be at risk from a white dwarf reaching the critical mass and detonating. However, our ability to survey these dimmer objects dramatically improved in 2013 when the European Space Agency's Gaia Space Observatory released its first massive catalog of information. Gaia is dedicated to precisely mapping the positions and movements of billions of stars in our galaxy. Through its meticulous efforts, scientists were able to identify approximately 13,000 white dwarf stars within a radius of 326 light-years, 326 light-years of our solar system. Despite this substantial number of potential candidates being identified, scientists remain overwhelmingly confident that none of them are scheduled to explode anytime soon. In this context, soon means within the next few 100,000 years, a period of several 100,000 years. Speaking of Betelgeuse, the massive red giant located in the Orion constellation, there are some scientists who have proposed that this star might detonate much sooner than the consensus predicts, perhaps even within the next few decades. This prediction is based on research that suggests Betelgeuse has a much larger physical radius than was initially calculated. If this accelerated timeline proves true, it would provide humanity with the unique opportunity to witness a relatively local supernova explosion within our own lifetimes, a true spectacle that has not been clearly visible from Earth in centuries. But even if Betelgeuse were to go supernova tonight, according to some of the most current and detailed scientific models, we would have absolutely nothing to worry about in terms of existential threat. The resulting shockwave traveling outward from Betelgeuse would take a considerable amount of time to reach our solar system, perhaps many years. Even once it finally arrived, the models suggest it would be traveling with an incredibly diminished force, a pressure weaker than the subtle push exerted by our own sun's continuous solar wind. In this scenario, it would not be our planet's magnetosphere or its atmosphere that primarily keeps us safe from the stellar debris. Instead, the protective sheath of the sun's heliosphere, the gigantic, teardrop-shaped magnetic bubble created by the solar wind that engulfs and shields our entire solar system, would be entirely sufficient to keep the incoming, diluted shockwave from a distant supernova at bay. The heliosphere acts as our first effective line of defense against the dilute matter of the galactic environment. So, there we have it. While supernovae are perhaps some of the largest, most violent explosions in the entire universe, through a combination of astronomical distance and the fortunate protective mechanisms of our own solar system, our patch of the galaxy has nothing truly existential to fear from them. The odds of us being hit by even the neighboring stars that are scheduled to go supernova, such as Betelgeuse, are incredibly small. It is true that Earth has plenty of localized cataclysms of its own, floods, earthquakes, and hurricanes that can bring devastation to a community in a heartbeat, and space remains a fundamentally dangerous place. But it is reassuring to know that of all the things we have to worry about, we can probably confidently cross planetary annihilation from a supernova off our list. The universe, however, remains stubbornly full of secrets. Some of the most incredible ones are currently hiding just beyond the reach of visible light, the light that our eyes and most traditional telescopes can detect. What if we were to tell you that more than 1.5 billion, 1.5 thousand million unseen objects ranging from distant galaxies and clouds of gas where newborn stars are beginning to ignite, to some of the oldest stars in our entire galaxy are sitting just out of our conventional reach, literally cloaked in thick cosmic dust? That is a frustrating, almost tantalizing thought, isn't it? Until now. That is, because thanks to the development and deployment of a remarkable instrument, the European Southern Observatory's Visible and Infrared Survey Telescope for Astronomy, better known by its acronym VISTA, we can finally begin to lift the veil on these hidden wonders. For the first time in human history, we have secured a truly comprehensive, panoramic infrared map of the Milky Way. This map possesses the power to pierce directly through the obscuring fog of space, the dust and gas, to reveal an unprecedented, clear view of our galaxy and the cosmos that lies immediately beyond it. In September 2024, September 2024, VISTA published the largest and most detailed infrared survey of the Milky Way ever undertaken. This monumental effort required a 13-year period, 13 years of dedicated observation, spanning from 2010 to 2023. 2023 carried out across 140 nights, 140 nights of telescope time. This project successfully captured around 200,000 images, 200,000 images, and generated a staggering 500 terabytes, 500,000 billion bytes of raw data. To give a sense of this volume, 500 terabytes is roughly the same amount of data it would take to stream a high-definition 4K video for nearly 3 years straight. Vista is an essential part of the European Southern Observatory's Paranal Observatory Complex, situated in Chile. Its primary focus, unlike specialized deep-field telescopes, is to rapidly and accurately map large swaths of the sky. By using Vista's infrared camera, which is known as VIRCAM, VIRCAM, the astronomical team was able to effectively peer directly through the dust and gas that saturates and permeates our galactic plane, successfully uncovering some of the Milky Way's most hidden and secret places. Traditional telescopes, including those that observe visible light, allow us to view space in what are known as visible wavelengths. These wavelengths, the spectrum of light, our eyes are sensitive to, range between about 380 nanometers, and 700 nanometers. These visible wavelengths are easily blocked by the tiny, opaque particles of cosmic dust that fill the galactic disk, creating vast, dark regions of apparent emptiness in photographs. But Vista is not like traditional telescopes. Instead of relying on visible light alone, Vista operates by detecting light in the infrared wavelengths, specifically targeting a range between 900 nanometers and 1,200 nanometers. 1,200 nanometers? Light at these longer infrared wavelengths has a crucial physical property. It can pass right through the obscuring dust clouds that completely block shorter visible light waves. This allows Vista to detect otherwise invisible objects, such as massive numbers of stars obscured by thick dust and even incredibly faint. Cold objects, like brown dwarfs, which are often referred to as failed stars that do not emit enough visible light to ever be seen with a traditional telescope. To appreciate the profound difference between viewing the cosmos in visible light versus infrared light, consider these two images of the Lobster Nebula, also known by its catalog number NGC 6357. The image on the left was taken in visible light. The image on the right was taken using Vista's telescope. We can clearly see that in the infrared view, the dust that heavily obscures our field of view in the visible image seems to virtually disappear. This revelation exposes what appears to be hundreds of thousands, or perhaps even millions, of previously invisible stars that were perpetually hidden behind the dark cosmic curtain. The incredible, comprehensive map we are discussing was created through the data collected by Vista, specifically through two massive, collaborative survey projects. These projects were the Vista variables in the Via Lactea survey, aptly abbreviated as VVV, and its companion, the VVV Extended Survey, or VVVX. The name Via Lactea is simply the Latin term for the Milky Way, underscoring the central subject of the investigation. The combined dataset from these two companion projects, which together form the complete Vista Infrared Survey, is so rich and detailed that it has already resulted in the publication of more than 300 scientific articles, fundamentally reshaping many aspects of galactic astronomy. Unlike other recent, often localized space maps created by other instruments, this survey by Vista stands as one of the most detailed and extensive ever made of our galaxy. It is the very first infrared survey to successfully cover nearly 80% of the Milky Way's total luminous mass, the mass that actively emits light. Furthermore, it provides the largest and most complete infrared catalog ever produced, specifically detailing our galaxy's incredibly dense central region. This unprecedented coverage and detail allows astronomers to study the inner workings of our galaxy in finer, more meticulous detail than was ever possible before. Crucially, this survey gives us a highly accurate, three-dimensional view, 3D view of the inner regions of the Milky Way, regions that were previously completely obscured by the thick, intervening clouds of cosmic dust. The area of the sky covered by the survey is immense, spanning an area equivalent to the size of 8,600 full moons. 8,600 full moons placed side by side. The resulting catalog contains approximately 10 times more objects, 10 times more objects than any infrared map published prior to 2012. To understand the scope of the project, it is helpful to visualize the structure of our home galaxy. The Milky Way consists of two main components: a massive, dense, bright, and slightly puffed up collection of stars at the center, known as the central bulge, and a much flatter disk of material that contains the spiral arms wrapping outward from the ends of the bulge. This image shows the vast area of our galaxy that was meticulously mapped during the survey. The red squares mark the central regions of the galaxy, the thickest, densest part, which were first observed by the original VVV survey and then meticulously reobserved and extended by the VVVX project. The other colored squares show the vast areas that were only observed as part of the extended survey. From this visual representation, it is clear that these surveys focused intensely right on the central plane of our galaxy, spanning a large portion of the galactic disk and encompassing most of the crucial nuclear bulge. So, what exactly has VISTA revealed from this monumental effort, Dr. Dante Meniti, an Argentinian astrophysicist who led this vast survey project, summarized the impact by stating, "We've made so many discoveries. We have changed the view of our galaxy forever. And while it would be impossible to cover every single discovery in our discussion, it is best to focus on some of the most spectacular highlights." As part of the survey work in 2015, VISTA turned its powerful infrared gaze onto the dramatic star formation region known as Messier 20, which is more commonly called the Trifid Nebula. This spectacular cloud lies approximately 9,000 light-years from Earth. When viewed in visible light, the nebula presents a beautiful, glowing spectacle. We can clearly see the pink hue resulting from the emission of light by ionized hydrogen gas, along with a surrounding blue haze caused by light scattered off dust particles from the young, hot stars embedded within. However, in this visible light image, the massive cloud of gas and dust is also completely obscuring the star-filled space that lies directly behind it. The cloud acts as an effective, dark curtain. Now, consider the power of the infrared view. Look at this second image, taken by VISTA's infrared camera. By peering directly beyond the foreground clouds, the camera reveals a whole swarm of new, previously hidden stars. This single image provided a profound scientific moment. It not only allowed us to see directly through the heart of the Trifid Nebula itself, but, by pure chance, it also revealed objects situated on the far side of our galaxy that had never been seen by human eyes before. To their great surprise, astronomers identified two faint, pulsating objects deep in the background as Cepheid variable stars, often pronounced Cepheid variables. While these stars appear in the image to be sitting just behind the edge of the Trifid Nebula, their actual, measured distance places them far, far away, about 7 times farther than the nebula itself, which had been so effectively blocking them from our visible view. This was a direct stunning demonstration of the power of infrared light to reveal the hidden depths of the cosmos. Cepheid variables are a particularly important and fascinating type of star. They are intrinsically unstable stars that possess a unique, predictable pattern. They brighten and then fade over a fixed, measurable period of time, which can range from a few days to a few months, depending on their absolute brightness. The very first variable star we successfully identified in modern times was Omicron Ceti, also known as Mira. It had originally been classified as a nova, a sudden flare-up, until 1638, when the astronomer Johannes Hevelius observed it repeatedly getting brighter and dimmer in a predictable cycle that lasted roughly 11 months. As for this newly discovered pair of stars, they are the only Cepheid variables we have successfully identified so far in this specific location, which lies beyond the central bulge on the extreme far side of our galaxy, and they are exceptionally useful to astronomers. You can think of these specific stars as a kind of cosmic yardstick or measuring stick that can be used to accurately gauge distances up to tens of millions of light years away. The reason they are such effective distance markers lies in a fundamental, known relationship between their physical properties. If you can accurately measure how long the star's pulsation period, the time it takes to go from its brightest point to its dimmest point is, then you can directly infer its absolute brightness, the star's true, intrinsic luminosity. Since this relationship is highly reliable, once the absolute brightness is known, you can then compare it to the star's apparent brightness, the amount of light that actually reaches Earth. By comparing the known true brightness to the observed brightness, the difference mathematically provides an extremely accurate measure of how distant the star is. This makes Cepheid variables vital tools for mapping the vast scale of our galaxy and beyond. The success of the VISTA survey, combined with a few reference points like these Cepheid variable stars, allows us to begin building a precise, three-dimensional picture of the immense scale and structure of our galaxy and the space that lies beyond its obscuring dust. The power of infrared light to reveal hidden structures is undeniable, leading directly to one of the most surprising discoveries about the Milky Way's core. Looking directly toward the galactic center, the crowded, light-years thick core of our galaxy that has always been shrouded from view by dense cosmic dust, a dedicated team of astronomers and data scientists methodically scanned the VVV data. Their goal was to find more of those unique distance markers. They successfully identified an impressive catalog of 655 candidate variable stars, showing the characteristic brightening and fading pattern. The next step involves sorting these candidates into their proper scientific classifications. Cepheid variable stars are not all the same. They fall into different classes, primarily categorized by their age, mass, and the chemical composition of their stellar atmospheres. The two main groups are Type 1, or classical Cepheids, which are typically young, massive, and rich in heavy elements, and Type 2 Cepheids, which are older, less massive, and found in the ancient, metal-poor parts of the galaxy. Through careful analysis of the light curves and pulsation characteristics, the team determined that 35 of the 655 candidates were definitively classical Cepheids. This was instantly a moment of massive scientific excitement. The long-standing conventional model of galactic evolution held that the massive, dense galactic bulge was an ancient, fossilized structure. It was believed to have formed extremely early in the galaxy's history, in a rapid, intense period of star birth known as a monolithic collapse. According to this model, the stars in the bulge should be predominantly elderly, at least 8 billion years old, 8,000 million years old, and the region should only contain the older Type II Cepheids. Finding even one single, young, massive, classical Cepheid in this region would have been unexpected. Finding 35 of them was a powerful challenge to the existing theory of the Milky Way's development. The pulsation period of a Cepheid star is directly linked to its true or absolute brightness. The longer the star takes to pulsate, the brighter it intrinsically is. By meticulously recording the precise length of the pulsation periods of these 35 stars, the team was able to infer not just their distance, but critically, their age. The results were remarkable. The analysis revealed that all 35 of these classical Cepheids were definitively less than 100 million years old. 100 million years old. Some of the stars were so young and luminous that their inferred ages suggested they may be as young as 25 million years old. 25 million years old. To truly put the youth of these stars into perspective, consider our own Sunday. Our sun is currently about 4.5 billion years old, 4,500 million years old. The youngest Cepheid found is only about 0.6%, 0.6% of the total lifespan of our Sunday. The presence of these extremely young stars proves that vigorous, massive star formation has occurred in the very heart of the Milky Way core relatively recently. This exploration into the properties of the Cepheids culminated in a secondary, major structural discovery. By mapping the precise three-dimensional locations of the 35 young classical Cepheids they found, the team was able to trace a completely new structural feature within the Milky Way. This feature was identified as a thin disk of young stars that stretches right across the galactic bulge. This is a crucial distinction. The discovery was not of a new arm of the galaxy, but a disk that intersects and is physically embedded within the much older, bulkier bulge. This thin disk was previously unknown and undetected in all past surveys of the region because, despite being bright, the intervening cosmic dust proved to be an impenetrable screen for visible light telescopes. The ability of Vista's infrared camera to pierce this cosmic veil was what finally revealed its existence. The fact that the structure is a disk, a relatively flat, rotating plane, and that it contains young stars strongly suggests it is part of the ongoing, dynamic evolution of the galaxy, rather than a relic of the ancient past. The new evidence of this thin disk, combined with the discovery of the young Cepheids, has led scientists to a fundamental new inference about the galaxy's history. It suggests that there has been continuous star formation along the galactic midplane, the central axis of the disk, for at least the past 100 million years. 100 million years. The core is not merely a static graveyard, it is an active factory. The discovery of this thin disk of young stars within the ancient galactic bulge is truly incredible because it completely overturns our previous thinking. We used to believe that the galactic bulge was exclusively an ancient feature of our galaxy's past, comprised solely of old stars that had formed in isolation, separate from the younger, actively forming stellar disk. The newly revealed evidence shows a young, thin disk, perfectly aligned with the galaxy's midplane and cutting right through the bulge. This indicates that the core is far more complex and involves a much longer period of dynamic evolution and ongoing star formation than we ever thought possible. It's also worth noting the limitations of this spectacular survey. The fact that we found 35 of these luminous, young classical Cepheids, all of which are less than 100 million years old, means there might be even younger Cepheids we haven't seen yet. Since these stars are so incredibly bright, they would be highly susceptible to the issue of saturation within the VVV survey images. Saturation occurs when a star's light signal is so intense that it completely overwhelms the sensitive detector in the Vista camera. This causes the camera to lose the crucial information about the star's subtle, rhythmic changes in brightness, its pulsation period, which is the key to identifying it as a Cepheid and determining its distance and age. Future, more advanced infrared telescopes will need to employ sophisticated techniques to accurately measure these potential, extremely bright young stars without this saturation effect. The knowledge that the core of our galaxy is still actively forming stars, and the realization that the galactic bulge is fundamentally more complex than a simple ancient blob of stars, shifts our perspective on the Milky Way's entire lifespan. It transitions the story of our home galaxy from one of a quick burst of formation followed by billions of years of stagnation to one of continuous, dynamic activity, a constant, slow burn evolution that is still happening today, 4.5 billion years after the birth of our own Sunday. The finding of that young, thin disk within the bulge reveals that the processes of galactic evolution are not always black and white. The formation of newer stars within the oldest region of the galaxy is likely a natural, dynamic progression of the Milky Way's development. But perhaps even more profound is a discovery made by the Vista Infrared Survey that points directly to the ancient, primordial heart of our galaxy. In 2016, for the very first time, a specific type of extremely ancient variable star, known as an RR Lyrae, pronounced RR Lyrae star, was successfully discovered right in the core of the Milky Way. This crucial finding was made by a team led by astrophysicists Dr. Dante Miniti and Rodrigo Andres Ramos, leveraging the exceptional ability of Vista to see through the central dust. RR Lyrae stars are vital astronomical objects. They are old, low-mass stars that have reached a specific, unstable phase late in their lives. They pulsate rhythmically, causing their brightness to vary over a fixed period, usually less than one day. Critically, these stars possess a known, reliable relationship between their pulsation period and their true, absolute brightness, meaning they function as a highly precise type of standard candle, a cosmic distance marker. They are typically metal poor, meaning they formed very early in the universe's history before subsequent generations of stars had created many heavy elements. Historically, this type of star is almost exclusively found in globular clusters, ancient, tightly packed, spherical groups of stars that tend to orbit the outer, halo regions of the galaxy. A typical globular cluster is an astonishing sight, a collection of tens of thousands to millions of stars, all bound tightly together by their collective gravity, existing as stellar fossils. They are among the oldest structures in the entire galaxy, containing a stellar population that can easily be over 10 billion years old, 10,000 million years old. The VVV survey found 12 RR Lyrae stars clustered right near the galactic center. This discovery strongly suggests that these stars are the remnants of an ancient, primordial globular cluster that did not survive intact, but instead dissolved right into the very heart of our galaxy. This finding carries immense weight because it provides direct evidence that might help astronomers decide between the two major competing theories concerning how nuclear bulges form in spiral galaxies like the Milky Way. One theory proposes that the nuclear bulge forms extremely early and violently in a galaxy's life. According to this model, the bulge grows through the violent merging and collision of numerous smaller, primordial structures, such as smaller satellite galaxies and those very ancient globular clusters. These ancient structures are torn apart by the immense gravity of the core, leaving behind their oldest stars, like the RR Lyrae, scattered throughout the bulge. The competing theory suggests that the nuclear bulge forms gradually over time. In this model, the formation is driven by immense amounts of gas being funneled inwards from the galactic disk toward the center, where it triggers intense, continuous bursts of star formation. While this theory is supported by the existence of the young classical Cepheids we just discussed, it doesn't easily explain the presence of those ultra-ancient RR Lyrae stars. Finding these ancient, metal-poor RR Lyrae stars deep within the galactic center suggests that the massive, bulging core of the Milky Way likely grew through the merging and tidal disruption of primordial globular clusters that were swallowed by the forming galaxy. This evidence, therefore, heavily supports the first theory that the bulge formed through the violent aggregation of ancient structures. So, this single discovery doesn't just hint at the deepest origins of our own galaxy, but it also offers compelling evidence into how these massive galactic bulges might form in other similar spiral galaxies across the universe. It suggests that galactic cores are built not just from gas, but from the digested remains of their oldest stellar neighbors. Speaking of these critical ancient stellar structures, VISTA's infrared capability was also instrumental in finding completely new globular clusters that had been hidden from view. As part of the infrared survey, VISTA successfully identified 2 new globular clusters in 2011. To understand why this is difficult, let us look at an image in visible light. On the right side of the image, we can see a known globular cluster called UKS1. It appears only as a faint, hazy red splotch, its light heavily reddened and obscured by the intervening dust. Prior to the new VISTA discoveries, this UKS1 cluster had been the dimmest known globular cluster in the Milky Way due to its extreme distance and the dust obscuring it. Now, compare this exact same patch of sky, but this time viewed in VISTA's powerful infrared light. Suddenly, the view transforms. We can clearly see what had been missing, much more faint and diffuse than the known UKS1. We can make out a distinct second globular cluster. This new cluster is visible in the upper left of the infrared image, and it has been cataloged as VVV CL00001. VVV CL00001. A second globular cluster, aptly named VVVCL00002, VVVCL00002, was found soon after, deep within the survey data. This small, faint group of ancient stars may represent the closest known globular cluster to the center of the Milky Way. This suggests that even the tightest, oldest stellar groups can persist very close to the crushing gravitational forces of the galactic core. The significance of these 2 discoveries is easily overlooked without context. Prior to these new findings by VISTA, there were only 158 known globular clusters in the entire Milky Way galaxy. For the VVV survey to identify 2 more of these relatively rare, ancient stellar objects is quite a significant accomplishment and a testament to the power of infrared technology. Within the galaxy's central, dusty regions, it is incredibly easy for both younger stars and the massive clouds of cosmic dust to effectively obscure globular clusters. This is especially true because their extreme age means their component stars are inherently dimmer and prevent them from shining as brightly as the young, massive stars in the galactic disk. But now that Vista has successfully revealed them, these newly found ancient features bring exciting possibilities for further scientific study and investigation. One of the tantalizing questions raised by the discovery of VVV-CL00001 is its relationship to UKS-1. In the image, they appear close together, but is this proximity merely an illusion of perspective, or are they physically connected? Scientists have begun to seriously wonder whether the newly discovered VVV-CL00001 is actually gravitationally bound to UKS-1. If this proves to be the case, then these two formations would represent the Milky Way's first known binary globular cluster, pair two ancient stellar systems orbiting each other. While we have found instances of binary clusters in other galaxies, such as those observed in the galaxy Centaurus A and in the Large Magellanic Cloud LMC, finding a pair right in our own galaxy would be invaluable. The study of binary clusters is essential because scientists theorize that when these gravitationally bound clusters eventually collide and merge, they produce the most massive globular clusters known in the universe, such as the famous Omega Centauri. Omega Centauri is so massive and unusual that many astronomers believe it is not a traditional cluster at all, but the surviving core of a dwarf galaxy that was long ago swallowed and disrupted by the Milky Way. Therefore, studying a binary cluster pair right in our own galactic neighborhood could produce truly amazing insights into this process of stellar merger, tidal stripping, and the subsequent formation of the galaxy's most massive stellar structures. While it remains a subject of ongoing speculation and further measurement, it is definitely a fascinating possibility to consider. In addition to those rare, ancient, globular clusters, the VISTA Infrared Survey also successfully identified a multitude of other types of star clusters. Unlike the globular clusters, which are old and tightly packed, VISTA found at least 96 new, open, or galactic clusters. Open clusters are the more common type of star grouping. They typically contain fewer, younger stars than their globular counterparts, and their gravitational binding is looser, causing them to disperse over time. They tend to be found primarily within the flat, gas-rich galactic disk. Like the globular clusters, these open clusters have been hidden from view by the cosmic dust that concentrates heavily along the galactic plane. However, VISTA's 4.1 meter infrared telescope has successfully lifted that curtain, allowing us to see them in their full detail. Take a look at just a few of these stunning images we now have of these objects. One of these newly discovered open clusters, cataloged as VVVCL00003, VVVCL00003, is much more difficult to distinguish in images compared to the tight, spherical formations of the globular clusters. In this section of the image, try to visually register the density differences in the distribution of stars compared to the surrounding background regions. This particular open cluster was found by VISTA about 15,000 light-years beyond the Milky Way center. This distance makes it one of the first open clusters of its kind to be definitively discovered on the far side of the galaxy. The ability to locate these clusters, regardless of the amount of dust obscuring them, is vital By pinpointing their location and age, astronomers are gaining a clearer picture of where and when star formation is occurring across the entire vast expanse of the Milky Way, allowing us to finally map the true, unobstructed geometry of our spiral arms. The sheer scale and depth of the VISTA infrared survey are truly staggering, representing a triumph in methodical astronomical mapping. By successfully covering such a vast region of the sky and cataloging more than 1.5 billion, 1,500 million individual celestial objects, this colossal data set has not only filled in numerous blank spots on our galactic map, but has already led to a rapid succession of fascinating discoveries that are actively rewriting our fundamental understanding of the Milky Way and the cosmic structures that lie both within and beyond its dense core. This massive undertaking is not the culmination of a decades-long field of study. Rather, it is unequivocally the very tip of the iceberg, providing the initial, essential framework for future astronomical breakthroughs. The comprehensive data meticulously produced by VISTA acts as a rich, three-dimensional tapestry. It includes the precise locations and intrinsic properties of key cosmic structures that define our galaxy's history and ongoing activity. For instance, the survey pinpointed the existence of 35 young classical Cepheids, the bright young measuring sticks, which, when mapped, effectively revealed a thin, young disk of stars embedded right within the ancient galactic bulge. Similarly, the data led to the crucial discovery of extremely ancient RR Lyrae stars, which function as telltale remnants that strongly support the theory of primordial cluster merging as a key mechanism in the bulge's formation. Furthermore, the infrared light pierced the dust to allow the identification of dozens of new, previously hidden globular and open clusters, filling in vital gaps in the census of our galaxy's stellar populations. This vast repository of information will serve as an absolutely essential foundation for future generations of telescopes and observations. The design and development of upcoming instruments are directly informed by VISTA's success and limitations. These next-generation telescopes are being designed with a focus on achieving significantly higher resolution, meaning they can distinguish finer details and separate closer objects and substantially greater sensitivity, allowing them to detect fainter and more distant objects than VISTA could. This progressive increase in technological capability will allow astronomers to expand significantly upon VISTA's infrared legacy, enabling them to delve deeper and more accurately into the hidden, dusty structures we now know exist. For the first time in human history, we possess the most detailed, three-dimensional map, 3D map, ever created of the Milky Way's physical structure and the objects embedded within it. This map successfully unveiled cosmic wonders that were previously unreachable because their visible light was entirely blocked by the thick, opaque clouds of cosmic dust concentrated along the galactic plane. This breakthrough is largely thanks to the unique properties of infrared light, which can penetrate the dust veil. Crucially, the full power of this galactic map is realized through multi-wavelength observation. By combining the robust infrared structural information from this groundbreaking VISTA survey with the incredibly accurate astrometric data, which involves the precise measurement of the position and movement of celestial bodies provided by the European Space Agency's Gaia mission Invisible Light, scientists are now gaining an unprecedented, truly holistic view of our galactic environment. Gaia's data provides the necessary time domain information, showing how stars have moved and how they will move in the future. VISTA provides the map of the structure, and Gaia provides the dynamic motion, effectively turning a static 3D map into a dynamic, four-dimensional, 4D model of the galaxy's evolution. This convergence of data makes this an immensely exciting time to be an astronomer. We are currently witnessing a dramatic flurry of new insights that are fundamentally reshaping our understanding of our own galaxy and the structure of the universe as a whole. VISTA's infrared observations have not only unveiled dozens of hidden star clusters and millions of previously unseen individual stars, but have also revealed brand new stellar nurseries, the massive clouds where massive stars are, currently being born and ignited. Furthermore, the synthesis of these findings has significantly broadened our understanding of the formation and dynamic evolution of our Milky Way. The evidence for recent, continuous star formation in the core and the signs of ancient merging structures show our galaxy to be far more active and complex, shifting the scientific consensus from a model of early, rapid formation followed by stability to one of ongoing, violent, and continuous evolution. Looking at the sky through these different wavelengths, from the short, high-energy visible light detected by Gaia to the penetrating, longer infrared light captured by VISTA, has unequivocally ushered in a new era of galactic exploration. The ongoing work by astronomers and data scientists, building upon the wealth of information provided by VISTA's definitive 3D map, promises a continuous stream of fundamental discoveries in the years ahead, revealing the full extent of the Milky Way's majestic and hidden structures. Having just navigated the vast, complex, and dusty structure of the Milky Way galaxy, it is essential to reset our perspective and re-examine the immense distances that exist even within the comparatively tiny scale of our own solar system. We are going to conduct a deliberate mental experiment to fully grasp the sheer emptiness of space by scaling down the dimensions of our solar system to something easily relatable to the human experience. For this conceptual exercise, we must first establish the scale factor. We will shrink the enormous actual size of our sun, a star nearly 1,392,000 kilometers, 1,392,000 kilometers in diameter, down to the minute size of just 1 millimeter. 1 millimeter. This is the size of a single fine grain of sand, or perhaps the tiny, sharp tip of a well-sharpened pencil. This massive reduction in scale, a factor of approximately 1.4 trillion, 1.4 followed by 12 zeros, is absolutely necessary to fit the vast light travel distances of our solar system into a physical space that is comprehensible. Let us begin with the sun itself. In our scaled model, the sun is placed right here, visualizing the sun as a 1 millimeter dot. It is a tiny, bright speck. Now, we must place the planets according to this tiny scale. The distance to the planets is a representation of the average distance from the sun as they orbit. Before we place the distances, let us pause to consider the size of the planets themselves at this scale. Since the sun is reduced to 1 millimeter, the planets also become incredibly small. Jupiter, the largest planet, would be about the size of a pinhead, roughly 0.1 millimeter, 0.1 millimeter across. Saturn would be slightly smaller than Jupiter. Our Earth would be reduced to the size of a microscopic speck of fine dust, smaller than 0.01 millimeter, 0.01 millimeter. Mercury would be barely visible, even to the naked eye, at this scale. This immediate reduction emphasizes the first critical lesson of the model. The sun contains almost all the mass and volume in the solar system, and the planets are merely minute particles orbiting it. Now we move to the distances. The solar system is often visualized as being evenly spaced, but this model immediately corrects that misconception. The closest planet to our Sun is Mercury. At the true scale, Mercury orbits at a distance of about 58 million kilometers. In our miniature model, that great distance translates to only 4 centimeters. Away, that distance is roughly the length of a typical matchstick, or 2 thumb widths. There is Mercury, a nearly invisible speck of dust, orbiting close to our grain of sand Sunday. The next closest is Venus, the planet often called Earth's sister world. Venus orbits our Sun at a scale distance of 8 centimeters, 8 centimeters away. The difference in distance between Mercury and Venus is marginal at this scale, highlighting how tightly packed the inner solar system really is. All the activity and heat occur in this extremely small, compact area. Then we reach the next planet, our home, Earth. In this model, our Earth, the microscopic dust speck, is placed at a distance of precisely 10 centimeters, just 4 inches away from the grain of sand that represents the Sunday. Life is sustained within this tiny, privileged zone. Moving outward, the planet Mars is placed farther out, at a distance of 16 centimeters. 16 centimeters. Beyond Mars lies the main asteroid belt, a dense, crowded region containing millions of rocky bodies. Within this belt, we find the dwarf planet Ceres, the largest object in the belt. Ceres is placed at a scale distance of 30 centimeters from our tiny Sunday. Even at this point, all the inner rocky planets in the entire asteroid belt fit comfortably within the span of about 1 foot, approximately 30 centimeters. The inner solar system is highly concentrated. The distances now begin to stretch far more significantly as we transition out of the rocky domain and move to the immense realm of the gas giants. This boundary is where the true emptiness of space begins to assert itself. Jupiter, the largest planet, orbits at a scale distance of 56 centimeters. 56 centimeters. From the Sunday, we are now already moving more than half a meter away from our tiny sun, and the space between Mars and Jupiter is vast compared to the spacing of the inner planets. The next gas giant, Saturn, is placed at a distance of 1 meter and 3 centimeters. 1 meter and 3 centimeters away. This is a critical point in the model. It marks the distance where we must physically step away from our initial position to continue placing the model planets. The distance between Jupiter and Saturn alone is larger than the entire distance from the Sun to Jupiter. Continuing toward the edges of the solar system, we encounter the ice giants. Uranus is found at a massive distance of 2 meters and 6 centimeters. 2 meters and 6 centimeters away from the Sunday. This distance is already more than double the distance to Saturn, emphasizing the enormous volume of space that defines the outer solar system. The last of the major planets in our solar system is Neptune. Neptune orbits our Sun at a scaled distance of 3 meters and 24 centimeters. 3 meters and 24 centimeters away. Even at this miniature scale, the distance to Neptune is vast, spanning over 10 feet from the Sun, making the light and heat from our 1 millimeter sun negligible at this distance. Finally, we arrive at the outer fringes of the solar system, the region of the Kuiper Belt, a zone of icy bodies and dwarf planets. Here, we find the best-known dwarf planet, Pluto. Pluto's orbit places it at a scaled distance of 4 meters and 22 centimeters. 4 meters and 22 centimeters from our 1 millimeter Sunday. This marks the approximate boundary of the main planetary system as we have defined it for this scale model. At this final, critical point in our scaled model, we have successfully mapped the entire known planetary solar system from the fierce heat near the sun out to the faint, icy orbits of Pluto and the inner Kuiper belt, all compressed within a span of about 4 meters. Yet, the question of proximity remains unanswered. If our sun, the heart of this entire system, is merely a single grain of sand, where exactly is the next grain of sand? This question, more than any other, visually unlocks the profound, almost overwhelming reality of the cosmos. The distance to the nearest star beyond our sun, Alpha Centauri, is staggering. In reality, Alpha Centauri lies 4.3 light years away, a distance that takes light, the fastest thing in the universe, over 4 years to cross. To find Alpha Centauri in our model, we would not measure 4 meters or 10 meters. We would have to travel a monumental distance of approximately 30 kilometers, a journey of nearly 19 miles. The fact that the entire 4-meter span of our planetary system, which includes all the planets in the Kuiper belt, is so incredibly minuscule compared to the 30 kilometers separating us from the next stellar neighbor, visually and mathematically underscores the primary characteristic of the universe, its vast, unimaginable emptiness. Even this 30-kilometer journey only takes us to the nearest star. If we were to continue mapping the true extent of the sun's gravitational influence, we would need to account for the Oort cloud, the spherical shell of icy debris that defines the outer boundary of the solar system. The Oort cloud extends up to 100,000 astronomical units, 100,000 times the Earth-Sun distance. In reality, in our model, the very edges of the Oort cloud would stretch out several hundred kilometers, hundreds of kilometers, farther, enveloping our planetary system in an immense, fragile bubble of ice and vacuum. The space that truly defines the universe is, by definition, the interstellar void. This realization of emptiness, however, connects directly back to the most unexpected discoveries we have discussed. We learn that this inherent cosmic void around us is not merely the standard, empty space between stars. We are currently residing inside the local hot bubble, a colossal cavity that was violently carved out by a sequence of 15 supernova explosions millions of years ago. These explosions swept the normal gas and dust away, making the space we occupy even less dense, even more empty than the typical interstellar medium. We are living inside a literal million-degree hole in the galaxy. This journey, from the microscopic scale of the solar system to the macro scale of the galaxy's evolution, has revealed two fundamental, opposing truths. On one hand, there is violence and destruction. The supernovae that created our hot, empty neighborhood are massive explosions that could wipe out a planet within 25 light years and scatter the contents of their star at speeds of 40,000 kilometers per evit, second 40,000 kilometers per second. This cosmic violence is the defining force of galactic evolution. On the other hand, there is intricate connection and discovery. The same destructive energy that carved out our bubble also triggered the formation of the thousands of young stars that now sit along its expanding boundary. And thanks to advanced technologies like the VISTA infrared survey and the Gaia mission, we can finally pierce the pervasive curtain of dust, the only significant non-empty element between us and the galactic core. These tools have allowed us to uncover the hidden architecture of the Milky Way, the young, active stellar disk, and the ancient, merging clusters of R Lyrae stars that tell the story of the galaxy's ancient birth. We have learned that the vast, empty space we inhabit is not static. It is a dynamic canvas shaped by ancient cataclysms and the slow, relentless sweep of dust and gravity. The elements that compose our planet, the iron in our blood and the calcium in our bones, were forged in the nuclear furnaces of those massive stars that died violently long ago, before our solar system ever existed. We are, quite literally, the remnants of those ancient explosions, drifting in a bubble created by their ultimate demise. The cosmos is defined by this continuous paradox: overwhelming emptiness interwoven with profound connection. We are safe from the violent stars due to immense distance, yet we are composed entirely of the material they created. We are nestled in a vacuum created by their death, while astronomers look through that vacuum using infrared light to find the youngest stars still being born on the bubble's perimeter, and the oldest stars that formed the galaxy's core. The next time you look up at the night sky, realize that you are not looking into a simple, peaceful, dark expanse. You are looking through a massive, hot, supernova-blasted cavity across 30 kilometers of empty space to the nearest star, at a universe that is far more complex, dynamic, and interconnected than any previous generation could have ever imagined.